So welcome to Data Science for Social Scientists. My name is Richard Landers. I'm the person who created this course initially. You may be watching this in order to do it as a self-paced course, or you might be doing this as part of a class that you're taking. But in either case, I think you're going to find it a really useful resource that it really addresses a need in the sort of the data science and programming sphere that we don't usually have, which is it's a course designed for people who already have some social scientific training, perhaps or even faculty or working in industry based on a psychology or sociology degree or political science or something like that, but yet are missing this core kind of explosion in quote-unquote data science that we've seen here recently. So that usually means you might know how to run ANOVAs, you know general linear model and some regression, you're able to poke around in SPSS or SAS or some other system, but you don't know R, and you definitely don't know something like Python. And those kind of systems, those kind of programming languages are the ones that you need to know in order to really take advantage of this sort of explosion in expertise and tool availability that we're now seeing really just dramatically transform our everyday lives. And I think it has the potential to transform research too, in a lot of very good ways. So that's really what this is about. If you haven't already had stats, there are some topics in this course which will be we'll move a little fast. We cover, for example, the entire family of ANOVA and repeated measures and multi-way, etc. in one class. Essentially, we cover all of the general linear model, all of the regression family in one class. This class is really, or this entire course is really intended to be a programming class. So I'm not going to talk really about stats. I'm not going to really talk about why you're doing most of these things, except in the cases where we're talking about brand new stuff. So toward the end of the course, for example, we talk about natural language processing. How do you take raw text data and turn it into a meaningful data set? So there I'll talk about the why a little bit more, but for most of the course we'll be focusing on mechanics. In terms of learning programming, it's really most useful to think of it like a language. You're actually learning to speak to computers. You're learning to instruct computers in getting them to do what you want them to do. So that's really the approach here. It's getting you to think like a person who can talk to a computer, and in this case, in R. So that's what we'll be doing. I'm going to go through a number of things in this first module video. This module video is a little unlike the others because this one is really customized specifically for the online version of this course that is released to the public. Normally in an in-person class, say for example, you are taking this in an in-person class or teaching in an in-person class, I would have icebreaker activities, and we would talk about people's preconceived notions about what programming is and if it's going to be hard. Most people say yes. So we're going to skip all that for this first video, and I'm instead just going to talk about sort of the core learning material. But in future weeks, you're going to be seeing my live lectures in a course that I actually teach regularly on programming and teaching people to learn R using this kind of framework. So this video will be a little different from the rest of them, just as a heads up. In today's video, what I'm going to talk about is first the kind of course materials that we have set up for this online version of the course. Two, going to introduce the idea of what is data science, why should we learn data science, why is that important for social scientists. Three, I'm going to walk you through a little bit about Data Camp, the major platform that we use to go kind of learn the nuts and bolts of the programming here. Next, I'm going to actually demonstrate a little bit about R and RStudio, which are two different programs you'll be using a lot of. Finally, I'm going to be talking about programming languages in general and kind of wrapping up then with just a brief little walkthrough of how the course is organized moving forward. So that's today. The Syllabus course website depends a little bit on whether you're doing this as a self-paced course or whether you're taking it for the purpose of you're watching these videos within another class. Most of all the course materials that I have are on datascience.tntlab.org. If you're taking this as part of another course, then you'll obviously want to look at their materials too, or perhaps even instead of mine. But all the materials that I use to actually teach this course to graduate students in psychology are available on datascience.tntlab.org. I've also customized the materials a bit for this online version, so they're not 100%, but they're very, very close to those materials. So if you want to just go through this on your your own without anybody holding your hand, you can do that. There's enough material here where you can kind of self-teach as much as you need. The recommended format I prefer, and the way that I teach it, is to split the course into multiple kind of pieces, to do some work at home, to do some work in a lecture environment, and to do some kind of project stuff on the side. It's what I would call a flipped classroom environment, where in the classroom you kind of work on applications for the most part and dealing with issues that come up, and that's in contrast to what's done at home, which is sort of that first exposure to programming. Programming is a language, so that means that one of the most important things to do is simply to practice talking to computers. As you learn to program, simply typing out, trying to get your thoughts into a format a computer can understand, that act is the most important thing that you can do. That is going to give you the most bang for your buck, so to speak. But just mucking around on your own, not so great. So if you can do this in a course environment, what I'd really recommend, the way I really most recommend doing it, is to muck around in that initial exposure and then have a live instructor there to answer questions in person during class time. So maybe you're doing it that way, maybe you're not, but I just wanted to kind of introduce that idea the way that I teach it, because I think it works really well. And I actually am able to bring a group full of psychology graduate students which have zero programming experience, and they've had maybe 1 or 2 courses in basic graduate level statistics using SPSS. And I'm able to bring them to a strong intermediate level in programming. So that's what this course is designed to accomplish, and I think you can accomplish it too using the materials I provided. So let's talk more about what it is we're talking about. What is data science? Why do we care? The word data science is a really confusing one because it's not really a thing. Data science as such doesn't really exist. Instead, it's used as a label for a whole wide range of different skill sets that people are suddenly finding very valuable. So a person that can call themselves a data scientist, even doing the same things as another person that calls themselves, for example, a statistician, the data scientist will usually make more money. So we're seeing that term getting thrown around a lot, but it doesn't have a very strong meaning. It can just refer to database decision making. In my field, industrial organizational psychology, there are graduate students in IO Psych who have job titles of data scientists despite learning everything in SPSS and just having kind of your standard skill set that an IO psychologist would have, but practicing it in the field. So this database decision-making, this ability to collect data, to interpret data, and to explain data to someone else, that's a core part of the data science skill set. So that by itself is called data science by some people. Other things, exploratory data analysis is very common in this space, to be able to just say, here's a data set, give me some information that I can use to make my business better or to make my research better. Predictive modeling is very common, to take some sort of Y variable and then predict it based on something else. In a lot of cases, this includes computer-assisted data analysis, because the kind of data analysis that you might do, in the kind of predictive modeling that you might do using some of these new tools might have like 50,000, 200,000, a million variables. And our traditional social science toolkit doesn't really have the sort of statistical chops to know how to handle that. As soon as we get into even a vaguely k approaching n situation where you have almost as many variables as you have cases, most of our traditional kind of throw ordinary least squares regression approach at it, it really just falls apart. So predictive modeling in these situations where we need a more brute forcey kind of approach to develop good generalizable predictive models, that's a really common part of data science too. Finally, programming. Programming in general is necessary to do a lot of the stuff in data science. That changes from year to year, though. Things that required programming last year don't require programming anymore, and that line will keep moving. But to really have the most power and control, you still really need that programming piece. I think in practice, when people talk about data science, they're really talking about predictive modeling that involves programming, usually in one of two languages, either R or Python. So that's usually what data science refers to, but I think it's really important to kind of demystify the term, because it's used in a way to sort of pull the wool over your eyes into thinking something really amazing is going on here, whereas in reality it just builds on the standard sort of statistical skill set that most social scientists already have, at least if you had at least a handful of stats classes when you were in grad school. So that's what I would call data science, and that the definitions vary a lot. I mean, there's really not a lot of agreement on this, but I think that using the term data science without understanding that it's really referring to all these different kind of approaches and can refer to any one of them, not even necessarily in combination, it's really important to truly understanding what this area can bring you, and also what you already know out of this area. That kind of terminology switcheroo occurs a lot in this space. There are a lot of terms in the data science sphere, which really means by people in computer science and in more technical fields, who have words for things that we already do, but call them different things. Like they have new words for stuff we already have words for. One of my favorites is algorithm. You hear algorithm all the time. Oh, they're using algorithms. Well, what is an algorithm? Fundamentally, an algorithm is just a step-by-step procedure that takes some sort of input and turns it into an output. It's not even necessarily a computer-based thing. I mean, algorithms don't have to be computer-based. An example I have right here that I think is really telling is an algorithm to calculate a mean. If you thought about, well, how do you calculate a mean step by step? If I were to give you literally a list from 1 to 50 or 1 to 10 or whatever, and you just went one by one, what list could you go through to calculate a mean? And importantly, it would have to be created in such a way that it didn't matter how many numbers I had. So regardless of the number of numbers I end up with, I can calculate a mean using this single step-by-step procedure. So that's an example of an algorithm. Here's and what I've written here is an example of the kind of process you might follow. This is using what you might call pseudocode, which is just me writing English language, regular words, as if I were a computer program. And you can see here, I input one vector of integers, and a vector just means a set of numbers. Integer, of course, is integer. And then process. Step 1, create two new variables, both with value 0, called m and c. So m is going to be kind of a running total, and c is a count. So then in step 2, for each value in the input vector, add that value to m, and then add 1 to c. After you've done that for each value, so it doesn't matter how many there are, final step, divide m by c and return that value. And that's going to be what we call a floating point number, because the decimal place can be anywhere in the number. It could be a 1.25975, it could be a 2.0, that point could be anywhere, so it's floating. That's what that means. But that's an example of how you think like a computer. It always has to be step by step. It always has to be step 1, 2, 3, etc. You can't just say, oh, look at all the numbers and add them together and divide by how many you found. You can't do it that way. You have to take it piece by piece, one after the other. And there are many different ways I could have created this algorithm. For example, I could have passed through it twice. I could have gone through it one time and added all the numbers together and then gone through a second time and counted them all. But that would be less efficient than the algorithm I created. So that means there are multiple algorithms for any given task, and that's a really important kind of point. But the broader issue here, again, you've calculated means before, but you were executing an algorithm without even knowing it. You were engaging in a step-by-step process. If I gave you a list of numbers on paper, you could calculate a mean, because in your head you're like, oh, add this one, this one, this one, this one, then count them, then divide. That's an algorithm. So don't let terms like that scare you off, and there's a lot of them, a whole lot. We'll tackle quite a few in this course. But I think it's very important that for every time you encounter a new term, you really think carefully, is this something I already do? And in many cases, it is. How does data science differ from statistics? And this is a complicated question. A lot of data science can be considered a subdiscipline of statistics called computational statistics. It's an area where there is not necessarily a convenient mathematical way to solve an equation, so instead you kind of brute force it. You try to figure out what the answer is by iterating over and over and over again, getting closer and closer to the answer every time. EM algorithm is something that a lot of social scientists have already used, especially that work on surveys. It's a way to impute missing data, and so it's very commonly used. You probably already use it right now, and that's an example of computational statistics. It's an algorithmic approach to dealing with the problem of missing data, so you don't have to do list-wise deletion or pairwise deletion or median imputation or all these other techniques. Pretty much all of which are not things you really want to do. So EM is one way, expectation maximization is one way to deal with that problem. So you may already be using some pretty complicated algorithms, perhaps without even realizing it. In the job market right now, a lot of people hire data scientists because they want someone to say, here's a pile of data. Now that you're within our organization, now that you signed all of our non-disclosure agreements, now there's all these reasons I can sue you if you share our secrets, can you just look at this giant database we've created and figure out something that will make us money? That's how a lot of data scientists are being hired right now. So that it's really skill sets created in the course of that pursuit that you're seeing become the most popular. So you're seeing natural language processing, for example, because there's so much text data everywhere, and companies are like, how can we use this text data to make more money? That's why it's become so popular very suddenly. Now, it's not to say there aren't researchers in the ivory tower working on this all the time, because there are, but that popularity jump has occurred because organizations are realizing there's value in their data, and computational power has become so high that a random person sitting at their desktop computer can now address some of these questions, which wasn't true even 5-10 years ago. In practice, though, a lot of people that get hired in that kind of position end up getting saddled with kind of this basic analytic job or data analytic job, where they're basically just said, oh, here's a survey, tell us how many people agreed to all of our statements. And a lot of people that try to get into the data science market, but without the true quote-unquote data science skills, they often get kind of pushed into that kind of role. So it's a really interesting kind of space to be in, because the real advantage, the new stuff coming out of data science, is very statistically based. I mean, it is very much about new ways to look at predictive modeling that are better than the ways that we've looked at before, or new ways to look at cluster analyses than ways we looked at before, or new ways to look at component analyses and factor analyses that we haven't looked at before, that are possible now because of advances in computational power. In the speed of a personal computer has gotten so fast that we can do a lot of stuff we couldn't do before. Many data scientists will get annoyed, though, if you tell them, you're just a statistician, really. All you're doing is really fancy regression. And that's kind of true and kind of not. Even the more advanced stuff that we have right now, like you might have heard of artificial neural network modeling or convolutional neural networks, the kind of thing that's being used to create self-driving cars. I might have heard the term TensorFlow. Some detractors will say that most of that deep learning artificial neural network space is really just really complicated logistic regression. Like, there's really not that much to it. It's just logistic regressions that feed into other logistic regressions. And when you tell data scientists that, they get really annoyed at you, because there is a lot of theory that's being built in that space, statistical theory and mathematical theory, that is being developed to try to better understand how to explore data. So it's, in terms of what the overall answer to this question is, how is data science different from stats? I don't know exactly how different it is. It seems to me in some ways that data scientists are really, people that call themselves data scientists that have the math and stats background, are really just statisticians working in this computer space. So maybe that's what they are. I don't know. But that general kind of theme of data science is what we'll be exploring. What these people that are calling themselves data scientists, what do they do, what do they use, and how can we use those lessons to improve our own research, or to go into practice, or to go into business, whatever it might be, post graduate school or as faculty. So that's what we're kind of exploring here. I like to define data science, and I've been going around a lot of different definitions, mostly to try to get you to think about it. I like to define data science as the engineering task of taking ill-defined or unclean information, quantifying it, and then drawing interesting, relevant, generalizable insights. And that can occur in a lot of different contexts in a lot of different ways. Many of the things that are being done, and I mentioned some already, like natural language processing or improved predictive modeling, can be used to improve psychological analysis or sociological analyses that are common already. And I think this is where the value is, potentially for us. But the problem is that there aren't that many translators. There's not that many people in the social science sphere willing to try to really deep dive into this stuff and then translate it back out for people. The number had a paper at Psychological Methods, for example, about web scraping a few years ago in a special issue on big data, and there was just such a small pool of researchers who really kind of deeply understood and understand what's going on in this kind of space right now. But I can tell you a secret. It's not that hard for the most part. Once you learn something like R or Python, it really is a gateway drug in a sense for all these advanced analyses that you can really dig very deeply into with relatively little new skill. Like, you don't have to sit down and learn a brand new course to understand how to do natural language processing. I teach you natural language processing once you, or at least the basics of it, once you have R down toward the end of this course in just a week. done. You can learn natural language processing. And that kind of scale is what's really attractive about this skill set. Once you have the basics down, it's not that hard to add new stuff. You just have to... and this will make more sense later. You just have to learn how the libraries and how the functions that you want to use work differently than what you're already using. But it's usually a pretty short jump. It's a pretty short leap to get from where you are to where you want to be after you have a good programming foundation. So that's where I want you to get at the end of this course. Many of these techniques create opportunities to analyze data in ways that we usually don't do it. Like natural language processing is a great example. The traditional way that you would analyze text data is by having humans read it and then make judgments and create numbers. Or not create numbers. If you're doing qualitative research, then you might end there. But with these new techniques, we can actually derive meaning and create a mathematical model out of text. And it's just a new way to examine theory in social scientific theory in ways that we previously just couldn't. And I think that's really exciting. When we talk about data science, it is important to distinguish it from data engineering. Data engineering is the more technical task of doing things like, well, how do we create a computer architecture to store big data? So say we're collecting information from a telescope, and we have just petabytes of data, just ridiculously huge amounts of data. How do we actually store that in a way that an analyst can get to it? That's a data engineering task. The data science task, even though it's an engineering task, is really about, well, once those data are available, how do we get them down and draw the insights from them? So they are distinct, and that's an important line. I think one of my favorite definitions of data scientists, and one which a lot of people resonate with, is that a data scientist is a person who is better at statistics than any software engineer and better at software engineering than any statistician. And I think that's a really great summation. It is very much an interdisciplinary crossing of skill sets. And I think the best data scientists also have a subject matter expertise in the area they're working in too. So as a social scientist, that's your subject matter expertise, and you need to bring in your already existing stats knowledge, but add in this software engineering piece. So that's where I think a lot of the value comes from. At this point, I would recommend that you pause this video and do the things you see here, which is create an account on datacamp.com, install R and RStudio, and install Git. So datacamp.com is the primary way that you get initial exposure to all the programming, and it provides a really convenient kind of place for you to practice coding. And the reason that's important is because, again, it's a language. R, which you're going to learn here, it has syntax, it has vocabulary, and the best way to learn and internalize all that is just to practice all the time. So DataCamp will actually give you real-time feedback when you're coding. You'll actually type an example out, you'll respond to a prompt, and it will tell you immediately if you're right or wrong, and it gives you that feedback. It'll also give you initial exposure to the new concepts that are really that we're going to be talking about in the video. So it's just a really great kind of one-stop shop for getting everything that you need. There's also two pieces of software, R and RStudio. There's two links to them here. They are different. R is the base programming language. RStudio is an environment in which you can use R, and you'll see the difference between those as I demonstrate them in just a minute. Finally, you should install Git, and you can just Google Git, download Git, and download that program. As soon as you install it, it should by default, RStudio and R will find it. You don't need to do anything other than install it. But Git is a really, let's say, headache-avoiding program to get because it will save you a lot of time later once you learn how to use it. It's an example of what's called a version control software, where it allows you to sort of save snapshots of your code that you write earlier, and you can revert back to those snapshots if you decide you've gone way down the wrong rabbit hole, which when you're starting to learn programming is actually pretty frequent. So Git will save you a lot of headaches later down the road. If you've ever had SPSS syntax that worked and then you modified it a little bit and you came back the next day and you tried to run it and everything broke, this is what it's designed to fix. That's what Git does. It keeps this sort of running log of all the versions of your software that you've written. So download those three, pause the video, make sure they're installed, and then we're going to step through them in the next slide. So in terms of the demonstration, we're going to go through two different platforms. One is Basic R, and two is RStudio. So there are really two systems here. If you go into, once you have everything installed, if you look in your start menu for R, then you're going to find two programs. One is going to be called RX64 or possibly RX86, depending on whether you have a 32 or 64-bit system. And the other is going to be called RStudio. If you load RX64, then you're going to be looking at a program that looks like this right here. This is R. R is what is a programming language, but this is an example of what's called interactive mode, where essentially you have the R platform running behind the scenes, and you can send commands to it and get output back out of it. So say, for example, in R right here, I can type 4 plus 4, and I get an answer. I get 8. I can do all sorts of mathematical operations. I can also do more advanced commands, which I'll show you in just a second. But the basic idea here is to think of R as an engine. It is sort of the underlying engine that runs all of your analyses. You're sending commands to it, and you're getting commands back. However, you're also able to store information while R is open temporarily in R. So, for example, I'm going to define a variable called x, and I'm going to use this little arrow symbol right here, which you pronounce gets. So this says x gets 2. Okay. Now, when I type x is now 2, which in turn means that I can do like x times 4, and I get the value 8 out, because x has been stored behind the scenes where I can't see it. So that's not super useful, because even though we can store values, we can't see them unless we query them, and so it's really easy to lose track of what's open and what's what you're actually looking at, and that's why people use the other program, RStudio. So if I close R, and move over into RStudio, you will see here is that same R that I was just looking at over in this tab called Console. The console tab is essentially that same engine. I can do the same thing here. You'll notice my X, though, doesn't exist anymore because this is a brand new install of R, or brand new instance of R, but I can still do all the same things that I did before. And so that kind of demonstrates to you what that is. Again, that's that engine. It's running behind the scenes on your computer, it's interactive, and it stores information. But what I want to point out to you is that when I save the value 4 to X, it now appears over here in this environment tab over on the right side of RStudio. And in fact, anything that I do on the left side here is going to end up getting saved to the right side. And because what RStudio does is it actually keeps track of all your variables for you. And that's super handy. So this is one of the major reasons why people use RStudio, is it's really it's just very convenient. One of the other advantages to RStudio is it keeps all this other information in the bottom right very handy. For example, let's say that I knew that I needed to use a command called filter. So it's going to run for a minute. Oh, I got all sorts of information right here. Filter, don't know what this is, all sorts of code. But what I can do is if I want to understand how to use it, I can type help filter. Whoop. And then in the bottom right, in the help tab, I now have all sorts of information about filter. So it keeps all these help files real handy and convenient, accessible to me within RStudio. So then as I'm coding, I can actually keep that open as a reference guide so that I can make sure that I'm doing what I think I'm doing. So let's try something else. I'm going to create something. You don't need to really worry about this right now. But I created a variable called Z, and I gave it 10 numbers. And then I created a histogram using the hist command. And you can see now that plot over here has appeared in plots. And if you remember back in the other R program that I was loading, there's nowhere for plots to go. So they actually open as a pop-up, and then you have to keep track of them or save them to a file somewhere, etc. RStudio just centralizes everything. You have everything in one nice, convenient environment all together where you can in a very serious way work on your code without being distracted by having to alt-tab over other places and save files, etc. So this is an example of what's called a GUI, a graphical user interface, GUI. And what a GUI does essentially gives you kind of an organizational structure around your code. SPSS is basically all GUI. So you usually don't dip into syntax. If you do, you probably found the syntax kind of hard to use, and it's really kind of goofy the way it's written. This is the other way around. Instead of it being the GUI being the primary place you do analyses and also the syntax is running under the hood, R, the code, is the main place that you're writing code, and the GUI just allows you to organize the output and reference guides simultaneously to that. So it's a little bit different way of thinking about it. When you use R, there's a couple different things to keep in mind. One, what we're using right now is called base R, which is the default set of packages, or the default set of commands that you can use in the programming language. And it's actually a pretty small set. There's actually a very limited number of things that base R can do. Instead, we have what are called packages. And what packages are is where a person that uses R has contributed their own code to create brand new functions and brand new capabilities for R, and then have released that to the public for free. So you can install packages at any time using the install.packages command, and then typing the name of whatever it is that you want to install. And what install packages will do is it will automatically contact what's called CRAN, the Comprehensive R Archive Network, which is a website. And you can see it right there, cran.rstudio.com. And what CRAN is a repository of all of those packages, and it just installed it. So now I've installed a package called dplyr, which we'll talk about a lot later in the course, and it's now accessible to me. And in order to run it, I do library dplyr, and now all the functions and all the capabilities inside dplyr are available in R. So functions, commands I didn't have before, I now have access to. This is a very fundamental way of working with R. You basically find the packages that do the things you need them to do, you install, run the packages, and then you use the things inside those packages, whatever they might be. And you can also use the help command to get extra information about the packages that you just got. So I just did help package equals dplyr, and you can see all of the new functions and all the new capabilities, and there's a huge number in this package, that I now have because I've downloaded and installed this program. So that's the basics of dplyr, or basics of packages. And we've already looked at R versus RStudio. One of the other things that you need to learn about RStudio is how to navigate it. These different pieces that we've been working in, these top left, bottom right, etc., these are called panes. And each pane is fully customizable. So you can see, here's a terminal, that's actually a command prompt, you might know that term, versus console, which is R. And we actually have a full history of all the commands we ran over here, connections, etc. This is all very customizable. You can move things all over the place. You can also go to full screen modes in order to look at things. Just a whole lot of capabilities. But each of these is called a pane by itself. You also have what's called a workspace. And what a workspace is basically where everything is organized. You can save it, including all of these variables in the top right. You can save all of that as a file so that you can open up your workspace later and have all the commands you ran and all of the history and all the files that were open all ready for you. So that's what a workspace is, and is a really common aspect of using RStudio. One of the things that you'll see me do a lot when I am using RStudio is you'll see the cursor jump around randomly. That's because I'm using using keyboard shortcuts or hotkeys. Control 1 jumps to this top panel up here. That's where we write scripts, which is a thing I'll introduce a little bit later. Control 2 jumps down to the console, and you can then imagine what Control 3 and Control 4 do. Control 3 jumps over to the bottom right, and Control 4 jumps to the top left. So you can navigate back and forth very easily between them. You can also write commands in the top left. So let's write in our commands dplyr, and let's see, what command could we use from dplyr as a demonstration. Let's say we're going to let's see if this will work. No, that won't work. So let's say that we have a data frame, and don't worry about these specific commands. I'll introduce this a little bit later. And it's going to contain 1 through 10, and then it's going to contain 21 through 30. So now I have a data frame. And I can run this command distinct, and what distinct does is it returns rows of a data set that are unique or distinct. So now I have a command. I have 3 sets of commands. But I don't necessarily want to run all of those down in the console because I'll forget what I did, and I could potentially lose track of all the commands and all the functions that I executed, and that's no good. We want to have, one of the major advantages to using R is having a fully reproducible workflow where you can start with raw data and end with complete analyses and figures and tables done from start to finish every single time that a person runs the program. So that creates reproducible science, the ability for somebody else to literally fully recreate what I did the first time. So to do that, I write scripts like this one, which now has 3 commands in it, and I can run these one at a time, also using keyboard shortcuts. One way to do it is to use this run command right here, and what run will do is it will take this line, it will essentially copy-paste it down here into the console and then run it. Alternatively, I can hit Control-Enter, which you'll see me do a lot. So if I hit Control-Enter, it sends line 1, Control-Enter, sends line 2, Control-Enter, sends line 3. So that's a keyboard shortcut that I use a whole lot, and you'll see me use a whole lot, but one I would really recommend that you also get in the habit of using too, because it's really just much faster than clicking Run over and over again. As you get more into programming, in R, or in any language, you really start to learn the advantages of keyboard shortcuts. They really save a lot of time after you start programming a lot, because you may need to jump back and forth between the console and the scripts at the top, 400 or 500 times in the space of a couple of hours, and clicking really adds a lot of time when you're doing that kind of thing. So get used to the keyboard shortcuts, and you'll see it a lot. I've already talked about command help. Git, you should already have installed, super useful. What I'm going to do right now, and whenever you create a project next time, which you'll need to do for next week, you'll do the same thing. You'll go to File, New Project. I'm not going to save. I'm going to create a new directory, a new project, and I'm going to call this Demo. And what a project is essentially a collection of all the files that you need in one place, and it has its own kind of environment, it has its own workspace, and it has its own panel locations and contents saved. So it's all that information in one place. But when I did that, there was a box that said, check to create a Git repository. Let me show you why that's so important. First of all, I'm going to create an R script, and I'm going to just go ahead and save it. Again, I'm using keyboard shortcuts here, Alt-F to go to File, and S to go to Save. I'm going to call this Demo. Let's say that I wrote a short R program. Types my first R program, and I'm very happy with this program that I just wrote. Okay, at this point, I would go to my Git tab, and I'd find the file that I just changed, which in this case is called Demo, and I click Commit. Now, what Git is essentially a computer program running on your computer. And what it does is it saves an archive of text files that you send to it based on what are called commits. So here I'm going to call this my initial commit because it's a brand new file. I'm going to check the file that I just had called demo, and I'm going to hit commit. It says, yes, you're done, one file changed, finished. And you'll notice that in the Git window, that file has now disappeared. Now let's say I was working on my file a little bit more, I was having lots of fun, I was testing out some cool stuff, and then when I went to run my program, oh no, it's broken. What do? Well, if that happens, then, and let's say I've saved, so now I can't even get back to the old version of my file, then what you'll see over here is, oh, now there's an M here that indicates modified for the file that I just saved. And if I click on the diff button, I can actually open up the archive of the previous version of my file, and I can use this revert button up here to go back to my previous saved version. So this is what I mean by version control, and you can see it cut all the way back to my original version. It basically saves snapshots of what your files looked like in the past, so that if you need to go back to them, even though you've saved it a few times, then you can go back. And this was stolen by Microsoft Word. You might have a feature called like Auto Recover or Auto Recover Versions. There's all sorts of names for it. But this is originally a technology used by programmers for this reason, so that you can experiment with code and then just revert back to the last known working version of your software. This will save you many headaches later down the road, and I strongly recommend you get accustomed to using Git so that you can recover old files if you need to. If you want more on Git, we actually don't really go into much depth in Git in this course, but there's a whole data camp lesson on Git that I would recommend if you want to learn more about it. But for now, just committing every time you have a major version of your software, like every time you're like, this is good, it's working, I'm happy with it, commit and make sure that the further changes that you make don't, destroy it. So that's the basics of R and RStudio and Git. The only other thing left on this slide to talk about is the R mindset. So what is that? Well, I think an important piece of learning to program is learning to think like a programmer. And there's a lot of specific ways that happens, and it's not going to happen overnight, but I've given here a list of kind of pointers for you as a young programmer, a novice programmer, that will help you kind of set down the right path. The first of those is you develop code. You don't write code. You develop code, and there's a big difference. Writing implies that you just put it down and it's done. You should instead think of writing code as a development process, the same way that writing a research paper is a development process. You don't just write one draft and say, I'm done. You instead go back, make sure, wait, that paragraph didn't sound right, I need to change it. That paragraph didn't sound right, I need to change that. I need to move these pieces around. That same basic process occurs in programming, except on a much finer level. You instead write, for example, 1 or 2 lines of code at a time. Run them, make sure they do what you think, and then you keep moving. And you move iteratively, piece at a time. You can spend a huge amount of time on a very small amount of code, but it can be worth it if that code, if you're confident that code is right. So there's a big time element associated with coding, and it's really important that you get in that mindset. You're not just going to sit down, hammer out some code, and be done. You're instead going to develop the code, test it, make sure it works. And I'll show you many examples of this in this course. 2, don't learn toolkits. It's really easy in SPSS, for example, to learn how to do ANOVA by clicking the ANOVA button, or learning how to calculate correlations by clicking the correlation button. And the same thing actually can happen in programming. In R, you can learn, this is the way I do an ANOVA. Don't learn that way. Make an active effort. If you find yourself doing that, don't do it. It's like learning survival phrases instead of actually learning a language. It'll get you to a certain point, but at some point you're going to hit a wall. If you start off learning survival phrases, though, it's going to be way harder later to fix the problem. So that's why you have to go in with the mindset of learning the language, not the toolkits. Third, think algorithmically, not procedurally. Remember the example I gave you before of inputs, processes, and outputs. Think that way. Everything in programming operates with an algorithm. There is some sort of input that goes into it, it does something, and then it spits something out at the end. That's really the same thing you're creating when you run your analyses for your research. Like you're essentially creating an algorithm that says, here's a data set, give me conclusions at the end. That's an algorithm. You're creating an algorithm, and you need to think that way, and it'll really help you understand the language. In terms of actual writing, a couple of specific points. Don't repeat yourself. There's a rule, sort of an unwritten, but often spoken rule in programming where if you need to copy-paste something more than once, don't do that. There's a better way. Anytime that you find yourself, for example, copy-paste and go like paste, 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 and then you change one number in like 10 lines, super common thing that people that don't know what they're doing really in Excel and Word and everything else do, you're going to learn how to get around that. You're going to learn a better way in this course. So anytime you find yourself copy-pasting, think, you know what, I bet there's a better way to do this, because there almost always is. Use and develop abstractions. One of the major concepts in programming is that you can develop a very specific piece of code for a very specific purpose, or you can develop a more general piece of code that is more flexible. And it's really useful to abstract out like that. So, for example, if you were doing a research task and you know, I need to calculate a mean of 4 numbers. So maybe you write an algorithm to calculate a mean for 4 numbers. But then next day, you need to calculate a mean of 5 numbers. Well, now you have to write a new algorithm in order to do that. But if you had just written an algorithm to calculate a mean for any number of numbers, you wouldn't have to write it again. So abstracting out the problem and thinking of a more general way to approach something is a really useful skill, and it's something you should pay attention to as you go. Is there a pattern that I can exploit in what I'm doing? Create data pipelines, not standalone code. What that means is to take this kind of approach I've been describing, which is to say, in your analytic pipeline, in your R code, you should start every single time with 100% raw data, freshly downloaded from Qualtrics, from an archival set, wherever it came from, and at the end have final tables, final figures, final everything. You create a pipeline that you can spit. You can even add different, totally brand new data in, and at the end, you'll have brand new tables, brand new everything, exactly what you need, without having to change any code whatsoever. That's like the golden dream here. So try to aim for that. Don't just write code to fix your problem. Create a whole pipeline. And finally, build test code. If you learn a new function, and you will learn new functions in your first data camp, try them out. If you say, well, wait a minute, what if I did blank? Don't just say that to yourself. Do it. Write the code and see what it does. There is no harm in testing things constantly. I find myself writing test code all the time, even when working on research projects. I think, wait a minute, I bet I could do this a different way. Let me test out a couple different versions and see what happens. And you'll see that as we go in this course as well. You'll see how I build test blocks as we go, or approach problems from multiple perspectives and try to figure out, well, which of these works best for our general case. So let's try this a little bit, thinking like a programmer. Remember our mean calculation algorithm, I already walked through it. Can you create your own algorithm to find the largest number in a set of numbers? And again, think inputs, outputs, step by step. Maybe pause the video, think about it. What I would do if I were going to develop this is I would say, well, wait a minute. If I'm a computer, I can only do one thing at a time. I have to go step by step every time. So what I'm going to do is I'm going to get my list of numbers, and I'm going to assume, number one, that the biggest number is the first. So if I have a list of 50 numbers, I'm going to assume the first one is the biggest. I'm going to assign that to a variable called max. And then I'm going to go through every single one of that in that list, and I'm going to say, well, is this one bigger? If it is, update max to be equal to that variable. If it's not, skip it. And do that, repeat that process for everyone until you're out of numbers. Now, if that's the way you thought about it, you're starting to think like a programmer. You're starting to think algorithmically, step by step. That's always the key. I will tell you that there is a decision I made for you in this course, which is that we're looking at R, and there are actually two major statistical computing programming languages, R and Python. There's actually many more than that, but R and Python are going to be the most common. R has much greater popularity right now with the social science crowd, just because I think it was introduced a little earlier. Python is more popular with the computer science crowd, but an applied data scientist will generally need or want to use both. You can get away with just one or the other, but there are definitely cases where something is easier in R or easier in Python. R is generally better for statistical analyses. It's built for stats. You'll see that as we go. It was designed by statisticians for this purpose. It's also really great at visualization, at least now. I wouldn't have said that 5 years ago, but these days it's really, really powerful platform for doing data visualization and very easy to put together really impressive looking stuff. Python is much better at project scale. So if you're going to be working with big data, if you're going to be working with text data, if you're going to be working in what's called a production environment, you would probably lean toward Python. But if you were in a production environment, you still probably wouldn't use Python because it's not super efficient. And what I mean by production, by the way, is what production is code that is used in real time in sort of a customer-facing way. So like when you call up your order history on Amazon or on some website, that's production code. There is code that is being accessed every time that you as a customer click on a button that causes that to happen. For us, there's not as many production cases, but the most likely it would be creating a web app. So if you were creating a web app, you might not want to use R or Python because it's a little bit clunky. We're still going to do it. We're going to create a web app in R in here, but it is a little clunkier than it would be if you were doing it in a better language. So anyway, all that is to say that there are different tools for different purposes. For most basic tasks, they're pretty similar. R is a little bit easier in terms of like data analysis than Python is, but Python is a lot more flexible. If you end up going into a kind of a data science career path, like if you're a graduate student and you're moving down the data science angle and you think you might end up alt-ac, where you're working in industry, not working as faculty, you'll probably need both at some point, and you might even need to learn more. And the real fortunate thing is about all of that, they really are languages, and they actually are very similar. in terms of how they approach problems. They're both what we call imperative multi-platform languages. So they have a similar kind of structure, a slightly different grammar and different vocabulary, but once you learn one, you'll find it way easier to learn the other, and in fact, you'll find it way easier to learn a whole bunch. Once you learn one language, it's like learning Romance languages. Once you know Spanish, it's easier to learn French, that kind of thing. Once you learn one programming language of a particular style, learning more is really easy. And we won't dip into that in here, but after you finish the course, I would really recommend you take a look at Python and just see, maybe it's a little more accessible than you think. And DataCamp, in fact, gives both R and Python lessons, so you'll be well set for either. In terms of the course itself, we do use the DataCamp platform. There's two pieces to this. One is the course structure, and one is the educator structure. If you're doing this on your own and as a self-paced course, or you're taking it as part of a course, then you'll be going through stuff like this right here, where you're going to go through individual lessons. This is the Introduction to R, which is the first one. When you go in these individual lessons, and I'll just show it to you very briefly, you get instructions about what to do, and then you get to type out the code on the right side and try it out. You can use the same keys that I was talking about in RStudio. You can press Control-Enter to send it down to the R console on the bottom and see what it does. And then once you're done, you hit Submit Answer over here. And it will tell you whether you did it right or not. If you did it wrong, it will give you feedback. If you did it right, it will say, good job, give you some more information, and move on to the next piece. If you're using this to teach a class, there's a really cool class framework here. You can actually see the pattern of students completing courses over the last semester that I was running this. You'll also notice that even graduate students tend to do things like in the 2 or 3 days before it is due. That's why it's got the multi-humps there going. But this actually gives a really cool kind of way to track what people are doing. In my courses, I assign weekly DataCamp lessons, and I can easily track it right here. So if you're teaching a course with this, I would recommend that you use that. It supposedly has Blackboard integration and integration with those kind of things. I couldn't get it to work, but maybe you will. But if you're just doing it in terms of the course, you're going to be operating almost entirely here. And that's especially what you're going to be doing for this first module. So yeah, that's basically it. If you're doing this as a self-paced, the basic path from here is you're going to be completing the modules in DataCamp, then you're going to be watching my lecture videos, then you're going to complete an applied project, and then there's a debriefing video where I explain how the project worked based on the material we covered. If you're taking it as a class, or you're teaching it in a class, maybe you won't do it that way, maybe you will. If you find something that works better, be happy to hear from you. rnlanders@tntlab.org. Otherwise, that's it. Good luck on your journey to learn R. It is really worth it. I'm very excited for you. Learning a brand new programming language is it really just opens your eyes to what's possible in a way that I don't think social scientists often get to experience. So I think you'll have a lot of fun. But that's it. Good luck.